Hello, good morning all. My name is Varun Kumar. I am here on behalf of NIWE and this presentation is on day-ahead solar PV power forecasting where we are targeting individual power plant modeling. The presentation which you have seen earlier is on the regional level forecast, and here now we are targeting how we can approach for a individual power plant in much elaborated approach. So again, the work is started. The work is just a part of a journey. We started with the GIZ and under the guidance of consortium of Overspeed, University of Oldenburg, Suntrace, and SGS. So the research question behind this presentation is to develop an indigenous day-ahead solar power forecasting system, and we are using both the physical equation involved actually scientifically on the site and the statistical approach for bias correcting and fine-tuning the results. So basically when we have a point forecasting model chain, we have a process flow diagram where we use the NWP data, numerical weather prediction data from the meteorological organization, and we use multiple NWPs because we have observed sometimes some NWPs work better and sometimes other. So we use multiple NWPs and we build multiple forecasting model chains. The forecasting model chains we will go in detail further. So forecasting model chains, we have different combinations of diffuse fraction, diffuse sky, DC model, AC model. So we will have all permutation and combination in place for the different forecasting model chains, and finally we combine the result and we give forecast on the basis of the optimum number of days which we obtain from the historic data to generate the combination coefficients. So here you can see we can have multiple NWPs, multiple solar power models, and finally the forecast is given as per the combination of all for the best accuracy which can be obtained. So when we talk about the numerical weather prediction data, we are using for this particular power plant, we are using NCM-RWF and ECM-WF data. And you can see the resolution is of 25 kilometer by 25 kilometer, which is much coarse resolution for an individual power plant. Considering the size of individual power plant, 25 by 25 kilometer space, we need to have a bias correction coefficient for the irradiation data. So what we do, we use a standard bias correction algorithms. We developed these algorithms in our facility at NIWE. So we try to use a standard fourth order polynomial function which is function of two variables, clear sky index and cosine of zenith angle. So clear sky index will give the attribute of solar irradiance, and cosine of zenith angle will give the attribute of the time of the day. So we will have a standard fourth order polynomial which will take into account of any bias correction which is required for the irradiation data obtained from the numerical weather prediction model, and it will be getting corrected with respect to the ground measurements. For ground measurements, we can take GHI measurements from the solar power plant where we are doing the forecasting, and if that is not available, we use the nearest SRRA station for that. As we have the largest number of solar SRRA measurement station in the world in India with NIWE. The other approach we used was of the artificial neural network approach, where also the input variable were same, clear sky index and cosine of zenith angle. And finally, we found we can see some results for the bias correction step, where we bias corrected the NWP for the ground measurements, because we want to mimic the same behavior as the plant is observing. So we try to first bias correct the radiation. So here you can see that with these plots, we found that for the optimum number of 20, 25 days, 30 days, the bias is almost coming to the zero value, or very close to zero. So that is what we are getting, that if we run the bias correction approach, we can get GHI value which is very close to what the plant is observing. So what we did here, we did this analysis for the 17th December to 16 June 2019, the 7 month of data. We used both the method, polynomial method and artificial neural network method, and we did the sliding window approach. So here that factor which was asked earlier as a question, that are we considering the cloudy days, clear days into picture or not? So here when we are using the sliding window approach, those are being taken care of, because it is taking the last 25 days into picture while correcting the solar radiation. Uh, After this, the next big thing which will affect our solar power forecasting model chain is the data quality. So for the individual power plant where we are working with, we got almost all data, but the DC power link was missing. Most of the places we found that SLDCs and regional load dispatch centers has not signed any agreement with the individual power plant for the transmission of DC power data. But DC power data plays a major role when we are considering soiling effect, and when we are taking into account that whether modules are being cleaned or not cleaned properly, what are the cycles of changing those things. So whenever when we are building model chains, when we have DC power, AC power all into picture, those losses will be calibrated in the fitting of the functions. When we receive the data from individual power plant, we do this kind of database management. It is not visible as though. So we have for each parameter we assign data quality, data status. Data quality can be considered as whether data is suitable for modeling or not, whether it is bad data, whether it can be used for forecasting but can't be used for further model development, like that. Now when we see about the model chain, after having the bias corrected NWP from the of the site, we use this model chain. Here you can see we considered two NWPs. We interpolated it to 15 minutes because we have to calibrate everything as per the Indian CRC norms, and the ABT meter data which we are receiving from the site is of 15-minute resolution. So we have to do the forecasting chain and 15-minute resolution. So the first the NWP data is interpolated in 15-minute steps, then bias corrected as I discussed, it is bias corrected with a sort of polynomial function in this paper. Then we use diffuse fraction model, tilt conversion model, and finally we got the GTI, and then GTI is converted to DC using Holt model or Bayer model, what we use in this paper. And finally, we combine the final AC power forecast. In earlier paper, you have seen in in that particular state, when we were doing the combination was at the NWP end. Here we are trying the combination at power end. After giving the NWPs as an input, we are finding the power values for both of the model chain, and finally we are combining at the power end. So this is the diffuse fraction model what we have used, the Chandrasekhar and Kumar. Here it is saying that what we are doing is we are calculating the clearness index from the GHI data what we are receiving from the bias corrected NWP, and we are calculating the diffuse fraction values using the Chandrasekhar and Kumar model, and finally we get the diffuse horizontal irradiance, and once we have diffuse horizontal irradiance and GHI, finally we get into the GTI using Klucher model by putting the tilt angles and other parameters in Klucher model equations. Once we get the GTI, the final the GTI goes into the module efficiency model, that is the DC model. And where here the DC model is actually the function of GTI what we getting, and the temperature, as the module power output depends very much on the temperature, and in some cases it is also suggested that we are trying to use that wind speed also at the surface level. Finally, we model, after getting the modeled DC, we use Schmidt-Sauer model. Schmidt-Sauer model models the intrinsic losses, ohmic losses, magnetizing losses, all losses into the picture. And finally, we calculate the AC power forecast at the power end. we can see here that if you see the results, uh, we are using two chains. I have shown here two model chains. We found out the RMSE values for NCMRW, ECMW both, and finally you can see after combining, the RMSE got improved by more than 14% from what RMSE percentage was of before. So that's why we combine the AC power at the power end, and we found that using the historical data set, these coefficients get trained every time the model is being run. So we found the for this individual for this individual power plant, we found 15 days was working better for this particular site. So final discussion, I can say that this was the development of indigenous day-ahead forecasting model, because we have used Indian data into the picture. And also we have seen that combination of physical and statistical techniques can give much better results than using physical things separate and statistical models separate. We have seen that the combination of different NWP models is improving the forecasting accuracy, and the reason for using two different NWPs was we observed the plots of different NWP combination coefficients. We found that while training the combination coefficients, we found that the weightage of individual NWPs vary differently. It is not like that one NWP is always dominating into the picture. So that's why we got into the approach of combining the NWP on the sliding window approach. Some fine-tuning steps is still going on. We are trying to use the dynamic aerosol information for further building clear sky models, and we are also trying bias correction coefficient on seasonal basis, and we are also trying to use other bias correction coefficients which are in the literature, like bin bias approach and non-linear approach. We can also test with advanced diffuse fraction models, because we have number of SRI stations into the picture. So some of the sites we can build our own diffuse fraction model, and similarly more fine tuning can be done if we divide everything on the weather classes. That so some of the meteorological agencies provide weather classes, but the edge for a solar forecaster is that he need to know that how to characterize a particular model for a particular weather situation. The issues and bottlenecks which we found during our model development phase were, the first, as I discussed, was the DC power data. The DC power data was found missing from the individual power plant. For example, and also the tilt angle changing information. The plants are not intimating us when they are changing the tilt angle of the solar power plant. So it becomes difficult for us in that case. The other thing is that the data power availability from the ABT meters. Most of the power plants are like, they can provide the data from the ABT meter not on the real time, but they can say it can be only possible to be given after 15 days. So we have to train the whole entire model chain using the SCADA power data, which requires a lot of cleaning on our end. And sometimes we have also visited many of the sites, and we have seen that they are not maintaining the pyrometer cleaning procedures. So when we are doing the bias correction, it sometimes affects the results for the individual power forecast. Thank you.